Humans are not static entities. We move, interact, influence, and are influenced, constantly shifting in response to the world around us. But what governs these movements? Why do we sometimes align seamlessly with the crowd and, at other times, stubbornly refuse to fit in? The laws of molecular dynamics offer an intriguing framework for understanding this. Just as molecules collide, bond, and disperse, so do we, whether in a bustling city, a social network, or a professional environment. As a child, Camilla watched dust particles float in sunlight, tracing their seemingly random movement. Some drifted in clusters, others veered off alone, defying the invisible currents guiding them. Years later, she realized these particles weren't just specks of dust. They were a perfect metaphor for people. Molecular dynamics studies how molecules interact under different forces. Their movement is not entirely random. It follows statistical laws that determine how substances mix, separate, and form new bonds. Human behavior operates in much the same way, a delicate balance between personal agency and the gravitational pull of social norms. Consider Newton's second law of motion. Force equals mass times acceleration. This isn't just for physics exams, it applies to everyday social navigation. Heavier particles, say a pack of rugby fans heading to a stadium, move differently from lighter, more agile particles, like schoolchildren darting between them. Recognizing these patterns allows for more efficient movement, whether you're dodging commuters in rush hour or figuring out when to strategically disengage from a conversation at a networking event. Understanding molecular movement also helps to explain crowd behavior. Take Brownian motion, the principle describing how tiny particles suspended in a fluid move unpredictably. Scale this up and you get diffusion, the process by which molecules spread evenly through a space. Now apply this to a train station. People move independently, yet clear patterns emerge. Some instinctively step aside to let others pass, while others charge ahead without hesitation. Despite these variations, the overall flow remains predictable, like molecules in a gas spreading to fill whatever space is available. For Pang, this realization transformed her view of public spaces. If people behaved according to predictable patterns, then they were not entirely chaotic. They could be observed, modeled, and understood, a reassuring thought in a world that often feels overwhelming. A widely accepted myth suggests there is a normal way to behave, to think, or to exist. But if molecular dynamics tells us anything, it's that true homogeneity doesn't exist, not in physics and certainly not in people. Ergodic theory explains that in any sufficiently large system, no single individual fully represents the whole, yet every individual contributes to the overall pattern. Translated into human terms, nobody is truly average, and yet everyone is part of the bigger picture. This contradiction highlights an important truth. While societies push for conformity, variation is not an anomaly, it's a necessity. No two dust particles move identically, and no two people perceive the world in the same way. If molecular dynamics teaches us anything, it's that progress relies on outliers. While most molecules move predictably, some break away, forming new compounds. This is how innovation happens, in nature, in science, and in society. Outliers challenge existing models, introduce new ideas, and venture into uncharted territory. The mainstream often resists change, yet paradoxically depends on it to evolve. Without outliers, nothing moves forward. And here's where ergodic theory throws in a delightful paradox. Given enough time, today's outliers become tomorrow's norms. Whether it's fashion trends, scientific breakthroughs, or social attitudes, what starts as unconventional eventually integrates into the broader system. If you want further proof that diversity is essential, just look at proteins. Each protein in a cell has a unique function. Some send messages, some bind molecules together, others build structures. A system where every protein tried to do the same job would collapse. Interestingly, even cancer cells demonstrate remarkable efficiency, adapting, evolving, and optimizing their roles with relentless precision. Unlike human workplaces, where egos clash and communication breaks down, cancer cells collaborate flawlessly. Not an ideal role model, but an undeniably effective one. So what's the point? Diversity isn't a flaw in the system, it's what makes the system work. The same is true in teams, friendships, and entire societies. At its core, molecular dynamics is about balance. Some forces pull us towards conformity, others push us towards individuality. Too much of either is limiting. The challenge is recognizing our unique trajectories while appreciating the patterns that connect us. Pang's insights provide a scientific foundation for understanding this dynamic. Whether in molecules or in human relationships, every movement matters. Every deviation shapes the system. And in the vast, interconnected network of humanity, individuality isn't a glitch in the system, it's the driving force behind its evolution.